talk about the different types of possible energy. We've sort of implied a lot of them, but we haven't really talked about it explicitly. We've got kinetic energy, which is the energy due to motion. We've got potential energy, which is the stored energy due to position. And we've also got something called thermal energy, which is the internal energy due to motion. So really, honestly, thermal energy, right, it's like when you heat something up, it gets hotter. That thermal energy is due to kinetic energy of the molecules inside the object. But here we're in this type of physics, we're talking about macroscopic objects, objects that you can hold in your hand. A glass of water is your object. If you move that glass of water across the table, you have changed its kinetic energy, and perhaps if you lifted it up, you've changed its potential energy. But you haven't necessarily changed its thermal energy, right? You change its thermal energy by adding heat to it, or by putting it in the fridge and taking heat away from it, and making the motion of the atoms and molecules less or more. So while thermal energy really is a type of kinetic and potential energy, when we talk about macroscopic objects, objects you can hold in your hand, we differentiate between kinetic, potential, and thermal energy. Those are the three total types of energy that you can have. And that's really important here to understand, because remember, we've got our puppy that we pull across the floor. We can lift it up as well. We can pull it across the floor and try to give it kinetic energy. We can lift it up and give it potential energy. But if we pull it across the floor and it doesn't go anywhere, then the energy we tried to give it had to go somewhere, because energy is a conserved quantity, and it went into the thermal energy of the floor, or the thermal energy of the puppy. We heated something up. So that's another place the energy can go. If we, quote unquote, lose energy from a system, we don't actually lose the energy, right? Because energy cannot be created or destroyed. It can only be changed in form or between bodies. We have lost it, quote unquote, lost it, by putting it as heat into the floor, into the puppy, that just can't be gotten back conveniently. We can't conveniently get it back. That's all it is. But it's still somewhere. So it's really important to understand. These are really our only three types of energy. And it's really important to understand that total energy, not total mechanical energy, but total energy, which includes kinetic, potential, and thermal, is always conserved for a closed system. And that is the most general comment that we can make about energy conservation. Energy is not created or destroyed. It is only changed from one form to another, or from one object to another. That just means that the total energy is always conserved for any closed system, or the total energy is always conserved for the universe. Can't make energy, can't get rid of energy. Okay. But then we have so that's one statement of energy conservation. Another statement of energy conservation is mechanical energy conservation. Mechanical energy is a subset of all energy. It includes potential and kinetic, but not thermal energy. Mechanical energy is conserved if, we just said, the work done by non-conservative force is zero, right? It's not always conserved. If you got friction, if you create heat, then mechanical energy is not conserved. So total energy is always conserved. Mechanical energy is not always conserved, but it is conserved if work done by non-conservative force is zero. What about kinetic energy? Is kinetic energy ever conserved? In other words, conserved means it doesn't change, right? To be conserved means it doesn't change, right? In other words, delta KE is equal to zero. Of course, kinetic energy can be conserved. We cannot change the kinetic energy. But we know from the work energy theorem that the total work done is equal to the change in kinetic energy. So if the total work done is equal to zero, therefore, kinetic energy is conserved. So I'm just showing these three different concepts of conservation. Conservation simply means something doesn't change. Conservation means delta quantity being whatever quantity we're talking about, delta quantity equals zero. That's what it means to be conserved. Just make sure you understand that, right? Delta of whatever quantity equals zero means conserved. And so we can talk about any type of energy being conserved. We can talk about like total energy being conserved, always. Mechanical energy being conserved, if the non-conservative forces do no work. Kinetic energy being conserved, if all the forces do no work. Now, all that being said, I just want to make sure that we understand the concept of thermal energy and heat, and be very careful about those definitions. Thermal energy is the energy in a system, within a system, or in a mass, right? We generally talk about single masses. If we heat it up or cool it down, that has to do with the thermal energy. But what is heat? Heat is not energy. You got to be real careful. Heat is the transfer of energy. How do I increase the thermal energy of my coffee? I add heat. I transfer in energy. How do I decrease the thermal energy of my soda? I put it in the fridge and I take away energy. I transfer heat out of the soda. Okay? So heat is the transfer of energy. It's not energy. In the same way, work is sort of a transfer of energy. Work is a way that we transfer energy from one body to another, or the way that we make a force change the energy of a body. So, if we have non-conservative force doing work on a body, again, just think concretely, friction is doing work on a body. Friction is taking energy away from a body. That energy goes into, or not goes into, that energy, well, it does, it goes into another body, right? Like, again, dragging a puppy across the floor, friction, we heat up the floor. We transfer thermal energy from the puppy to the floor. We heat up the floor. So while the work done by the friction is negative, we can talk about the heat transfer, therefore, is positive. If friction does negative work, we are transferring positive heat to the floor. So we can talk about Q is defined as heat, and we say that define the work done by non-conservative forces, at least if they are indeed transferring heat, if they're just heating up things, then we must say that work done by non-conservative forces is minus Q, because again, if the non-conservative force does negative work, it means we are transferring positive thermal energy, heat, from one body to another, so there's a negative sign, and so we get is minus Q. What does that mean? Right? In this case, that means let's assume that the mechanical energy goes down because we're losing energy as heat. That negative sign is what tells us it goes down. The quantity of heat is Q. Super simple example. Let's just take, let's say we have a box sitting on a floor, and I give that box a push, so it's got an initial velocity of v0. Friction is going to slow that box down. It's going to take it to a stop, so it slides across the floor until friction stops it. Where did the energy go? The energy went into heating up the box and the floor. How much heat was generated? Well, I didn't lift it up, so there's no potential energy we have to take into account. The initial kinetic energy is 1/2 mv squared. The final kinetic energy is 0. So the change in mechanical energy is final minus initial is 0 minus 1/2 mv squared. And that must equal minus the heat generated. The heat generated, therefore, in this case, is positive 1/2 mv squared. See how the signs work out? We have generated that much heat, and that is what has now heated up, changed the thermal energy of the box and the floor. All right, that's all we got for energy conservation concepts. Now we'll do some problems.